Today we're going to discuss systems of inequalities in two variables. The systems piece here means that we have more than one. So we might have two inequalities, we might have three inequalities, we might have four inequalities. The two variables piece means that we're going to have to represent our solutions graphically. Some issues that we need to discuss with the graphic is, are we going to dash our curve, or are we going to have this be a solid curve? Before we get into a system, we're first going to use a single inequality in two variables. We're going to use y is less than or equal to 2x plus 3. We're going to have to represent this solution graphically. Graphically, we would show the line y equals 2x plus 3, which has a slope of 2 and a y-intercept of positive 3. We're going to make this a solid line because equals 2 is valid. So solid would be equals 2 is good. We then need to decide whether we're shading above or below. I don't like to create a rule here that says when we have less than, we shade below, when we have greater than, we shade above. I would far prefer testing a solution. I would test a solution like 0, 0. When I plug in 0 for y and I plug in 0 for x, do I get a true statement? 0 is less than or equal to 3, and as a result, that 0, 0 will be part of my solution, and I should shade in that region. I can test any point as long as the point is not on the given line. If I get a true statement, I should shade with. If I get a false statement, I should shade on the opposite side of that point. A second example that we're going to do is y is greater than x squared minus 3. So in this case, we're going to graph our solution. We're going to graph the curve y equals x squared minus 3, which is a quadratic that's been shifted down 3 units. But in this case, we're going to dot that curve in. And the reason we're going to dot or dash is because equals 2 is not included. We then need to decide whether we're going to shade above this quadratic or below this quadratic. I don't like to make a rule about being above or below, but I would test a point. An easy point to test is the origin. When I plug in 0, 0, I do get a true statement, and as a result, I'm going to shade with that point. The shading is going to represent my set of solutions. There are infinite many solutions. There are not all real solutions. And these are all data points that create a true statement here. There are infinite x, y values that I could plug in to give myself a true statement. Finally, in example 3, we're going to bring these together. Y is less than or equal to 2x plus 3, and y is greater than x squared minus 3. We're going to graph both of these. We need to be careful to dot when appropriate and make solid when appropriate. The line here is going to be a slope of 2, y-intercept of 3, and that's solid because of the equals 2. The quadratic is going to be dotted or dashed. It's a x squared that's been shifted down 3 units. These two curves are going to intersect twice. I likely would test the point here 0, 0, but I'm going to choose a different one. I'm going to choose 0, 4. So when I plug in 0, 4 into my first inequality, I get 4 is less than or equal to 2 times 0 plus 3. I get a false statement here. As a result, my data point of 0, 4 is on the wrong side of the linear graph. When I test 0, 4 for the quadratic, I would get 4 is greater than 0 squared minus 3. I get a true statement. So my 0, 4 is on the correct side of the dotted or dashed quadratic, but on the wrong side of the linear. I should be shading in this region right here, which will represent my solutions. One thing to note here is the points on the quadratic are not solutions, but the points on the linear are solutions. The points of intersection would not be solutions because they would satisfy for the linear, but they would not satisfy for the quadratic. We're now going to get into an example. I think you should pause to write this and read the problem thoroughly at this point. So the gist of this is that we have two factories producing 3 types of material, low, medium, and high. These 2 factories produce them at different rates, which are given above. They also charge different amounts. We, as the owners of this manufacturing company, are trying to minimize our costs and yet meet the criteria of the low, medium, and high grade that we desire. The first thing we're going to do is define our unknowns. Those are typically going to come from the question here: how many days should each factory operate to fill orders at a minimum cost? So I'm going to say A is the days for factory A to operate, and Y is going to be the days for factory B to operate. I'm now going to come up with equations, or rather inequalities. I'm going to come up with one inequality for low, one for medium, and one for high. The inequality for low will be determined by factories A and B, how much they're going to produce and how long they're open compared to what we desire. Factory A is going to give us 8 tons per day. Factory B is going to give us 2 per day, and we desire at least 24 tons. Similarly, for medium, Factory A will give us 1 ton, Factory B will give us 1 ton, and we desire at least 6 tons. Finally, for the high grade, Factory A will give us 2 tons per day. The second factory will give us 8 tons per day, and we desire at least 30 tons. Some other stipulations here is that A needs to be open either 0 or a positive amount, and factory B needs to be open either 0 or a positive amount of days. We're not worried about any quadrant besides the first quadrant here. Another equation that's going to be relevant here is the cost. So the cost is going to come down to $2,000 per day for A and $4,000 per day for B. So we're going to write an equation here that would say 2,000x plus 4,000y, and this is the quantity that we're going to want to minimize. I'm going to graph these inequalities using Desmos. Here you can see a visual representation of the 8x plus 2y, of the 1x plus y compared to 6, and then finally the 2x plus 8y compared to 30. All of these lines are solid because equals 2 works, and all of these are being shaded above. What we're really looking for is this intersection of these points in the first quadrant. So one point that we are going to be worried about is 0, 12, down here at 2, 4, down here at 3, 3, and then finally the intersection with the x-axis occurs at 15, 0. We're going to need to test all 4 of those points to find where we have a minimum cost. Based on a rough sketch, the points that I care about are going to be roughly shaped like this. I care about 15, 0. I care about 0, 12. I care about 2, 4. And finally, I care about the point 3, 3. Shaded above that is all other possible solutions, but they will not help me minimize cost. I'm going to label these points 1, 2, 3, and 4. I'm going to determine the cost at these various points. The cost at point 1 will be $2,000 times 0 days plus $4,000 times 12 days, which will give me $48,000. The cost at point 2 will be $2,000 times 2 days, $4,000 times 4 days, which will give me $20,000. Point 3, 3 days for each, which will give me $18,000. And finally, $2,000 times 15 days and 0 days for our second option will yield $30,000. Here we can see that the best option will be the cost for the third point, which is 3 days of each factory. So our solution here would be 3 days at factory A and 3 days at factory B. Let's just verify that we met our criteria. For the low grade, we will use 3 and 3, which would give us 24 plus 6 needs to be greater than or equal to 24, and it is. 3 plus 3 needs to be greater than or equal to 6, and it is. And then 2x plus 8y, we would get 6, plus 24 needs to be greater than or equal to 30, and it is. We actually have here, for low grade, we have an excess of 6 tons. But the others are meeting the criteria spot on of 6 tons for medium, 30 tons for high, and we're actually getting a 30-ton load here for the low grade. As a manufacturer, that's probably a good thing. However, possible negatives could be, where do we get rid of those additional 6 tons? How do we sell that? Where do we store it? But based on the criteria that we have of being greater than 24, this is going to be the most desirable situation. I'm going to leave you with a similar question here. 2 oil refineries produce 3 grades of gasoline. In what fashion do we need this gasoline to be produced in order to minimize cost? Good luck.